Hello, welcome to chapter 7. Today we're going to do a little bit of introduction to what we're doing in this chapter. It's actually a relatively short chapter, but today we're just doing an introduction to these things called sampling distributions. So this is section 7.1. So set up a scenario here. I want to find the average U.S. household income. Okay, household income average. What can I do? Well, how do I do it? Can I survey every single household in the U.S.? Probably not. Doesn't seem realistic. So we need to find ways to estimate population parameters. Okay? And that's where samples and sampling comes in. Okay? We've learned what a parameter and a statistic are. A parameter is a number that describes some characteristics of the characteristic of the population. So when you're dealing with these, there's different types of them. We'll get into the main ones in a second. A statistic is a number that describes some characteristic of a sample. So reminder, parameter goes with the population, sample goes with a statistic. Now here's our main ones that we're going to be looking at. Sample statistics are also called point estimators, by the way. If you hear the term point estimator, it's just estimating the corresponding parameter that goes for the population. But our common statistics, mean. So sample mean is X bar. The population parameter would be mu. Done a lot with those. P hat is the sample proportion, so the proportion of this. It estimates P, which is the population proportion. And then S is the sample standard deviation that estimates sigma. All right? So let's look at a couple different scenarios that might require us to look at those things. So here's my first one. It says identify the population, the parameter, the statistic, the sample, and the statistic in each of the following scenarios. I've got one here. First one, it says each March, the government's current population survey asks detailed questions about income. The random sample of 60,000 households contacted in March had a mean total income, money income of 69,677 in 2011. The median income was lower, of course, at 50,000. So what we're looking for is, what is the population? What is the parameter that goes along with it? So the population, in this case, would be all households in the U.S. So they're trying to find that information about all households. So all, we'll say U.S. households. What is the parameter that goes along with it then? Talking about mean income. So our parameter would be mu equals the true mean household income. Not the estimated, the true. So I want to list that. Now, it also asks us to find the sample. So what we're going to do is we're going to talk about what the sample would be and what is the statistic that we're finding. We should already know that's going to be X bar because that goes along with mu. But the sample was the $60,000 or 60,000 homes contacted in March of 2012. So it's 60,000 homes contacted. And we would have X bar is our mean, which we actually got. We can actually state X bar is 69,677. Okay? So a little review of populations and statistics, or parameters and statistics. I'd like you to try one on your own here. And that is, right here. Identify the population, the parameter, and the sample, and the statistic that goes along with this one. It says a Gallup poll asked 515 randomly selected U.S. adults if they believe in ghosts. Of the respondents, 160 said yes. So why don't you pause it and see which one of the parameters and statistics go along with the appropriate population and samples. All right. So the population in this case would be all U.S. households again. That's where it's coming from. And the parameter that we have or that we're looking for would be a proportion. It is a P, a proportion of adults who believe in ghosts. So that leads us to our sample. Our sample happens to be the ones that we actually surveyed. It would be the 160. Actually, no, it'd be the 515. Only 160 said yes. So it's the 515 randomly selected U.S. adults. And along with that comes a statistic. In this case, it's p hat, because it's the proportion who say they believe in ghosts, which ends up being 0.31. So it's p hat that estimates the parameter. Now, I want to go back to our income one. How can X bar of 69,677, based on a sample of only 60,000 households, be an accurate estimate of mu, when we know that we can figure out that there's 121 million American households out there? How can the 60,000 be actually a good estimate? After all, a second random sample might get you a totally different value. That's natural. That's a thing called sampling variability. Okay? Sampling variability is something we've talked about. It refers to the fact that different random samples of the same size from the same population produce different values for a statistic. So how can we actually find one that's the most accurate? It's never going to be 100% accurate. Because if you look at this, you might get a value that's, like we just had 69,000, that might be our X bar. You might get a different sample that has over 75. You might get a different sample that's down at 50,000. And you can keep doing samples, and you can keep doing samples and getting new X bars. And you know what? What's going to happen the more you do? It's going to get closer and closer to the true mean if you really did it with everybody. Okay? And that is what we like to call a sampling distribution. Do I have that on here? Yes. A sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples. And that's what I want to underline here. If you could really find all possible samples of the same size, that would ultimately make your sampling distribution. Unfortunately, we can't always do that. We don't have the means to do that. And it's just not realistic. But we can find enough of them to get a better estimate. Now, to get a truly trustworthy estimate of an unknown population parameter, we want to start by using a statistic that's considered an unbiased estimator. Okay? A statistic is used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution, so if you're trying to find the mean of all those means that we just talked about, is equal to the mean of the actual, like the actual mean. That's considered an unbiased estimator. Again, not real easy to find. So to get a trustworthy estimate of it, we want an unbiased estimator. But unfortunately, using unbiased estimator doesn't guarantee that it's also that the value of your statistic will be close to the actual parameter. But the larger the random samples that we take tend to produce estimates that are closer to the true population. Size matters when it comes to samples, or the number of samples. So we prefer larger, more samples so we can get closer and closer. I'll give you a quick visual. Again, we're just touching on the basics here. But we have, on the left side, we have sample size of n equals 5. Okay? We have a sample data. We have a distribution of the means. We have a mean right here. We have a mean right here. We have a mean right here. These are three different things where we look at data that with this n equals 5 where we have the same mean, but it's really hard to tell. Like, look at this thing. This sample data of 5 is not great. Yes, it has that mean, but is it truly a good estimator there? So if we take a sample size of 25, well, what happens? It's starting to actually look more like what it should look like based on the population. It still has the same center, but it produces less variability. You can see here less variability and starting to see the actual shape. So the variability of a statistic is described by the spread. We've talked about that before. And it's mainly determined by the size of the random sample. Larger samples give smaller spreads. The spread of the sampling distribution does not depend much on the size of the actual population, but on as long as the population is at least 10 times larger than the sample itself. Okay, so just a reminder, we want our n to be less than 10% of the population. Now I want to finish up here and state that in many cases it is obvious which statistic we should be using as our estimator. Like if we wanted to estimate a population proportion of P, we're going to use P hat. If we want to estimate the population mean, we're going to use X bar. If we want to estimate the population standard deviation, that's where we do S or S sub X. Okay? But there's also some times where it's important to look at what is the best one to use in a situation. So decide which estimator to use when there is several reasonable choices. Consider both bias and variability. We've talked about bias before. What bias does is it changes the accuracy of something. Something is causing our results to be inaccurate. So bias means that our sample statistics do not center on the population parameter. In other words, our estimates are not accurate. The other thing we look at is variability, which we just talked about. High variability means that repeated samples do not give very similar results. They're very spread out. In other words, our estimates are not precise. So I just have a bullseye visual here. If you have high bias, meaning you're not quite accurate, but low variability, it is all centered around the same sort of area. It's just not where the population parameter is. If you have low bias but high variability, these are all centered around that center, the true thing, but they're just very spread out. If you have high bias, meaning it's not accurate, and high variability, that's not real accurate and not real centered at one point. And what's the ideal is no bias and low variability. Not real spread out. That's where we want it to be. So how do we avoid bias? You can't always 100% avoid it. However, based on Chapter 4, a big one here is good methodology. So we want to be able to look at our methodology and make sure it is sound. Like we talked about simple random samples. SRS is a common one that's good. I think worth noting is good questioning. Oops, I totally biffed that one. Good questioning. Okay, we don't want to have questions that are going to be leading to one response. How do we reduce variability? Well, that's what we just talked about. Large sample size. So we want a lot of samples if we're dealing with sampling distributions. So what I want to do is finish up with one scenario here. It says, to determine how much homework time students will get in class, Mrs. Lin has a student select a simple random sample of 20 chips from a large bag. The number of red chips in the simple random sample determines the number of minutes she will give them to work on homework. Mrs. Lin claims that there are 200 chips in the bag and that 100 of them are red, so half of them are red. But when Jenna selected a random sample of 20 chips from the bag without looking, of course, she got 7 red chips, but you'd think she'd get 10 if it's really half and half. Does this provide convincing evidence that less than half of the chips in the bag are red? Well, let's break it down. Question A says, what is the evidence that less than half of the chips in the bag are red? Well, don't overlook the obvious. This is a proportion. From our sample, our p hat was 7 out of 20 were red. That is 0.35. And note that 0.35 is clearly less than 0.5. That's our reasoning. Is that enough evidence? Well, we're going to look a little bit more closely. Provide two explanations for the evidence described in Part A. Why would it be less than 0.5? Option number one. Maybe you're thinking Mrs. Lynn is lying. And actually, less than half are red. Let's assume the best, but that could be the option. That's kind of what we're thinking here. There is another thing that could be the reasoning, and this is oftentimes more typical. We're trying to see if this is the reasoning. It's just bad luck. Okay? She could have gotten it just by sheer luck and the idea of sampling variability. Okay? So we're going to look into it and see what data tells us. So we use a technology to simulate. We've talked about simulations before. Simulate 500 simple random samples of size n from a population of 200 chips, where 100 are red and 100 are blue. So we set it up how she says it is. The dot plot shows p hat, which is the sample proportion of red chips for each of the 500 samples. So let's use this. Now, question C says there's one red dot on the graph at 0.8, so that's way over here. What does this represent? Remember, that represents one simulation where 80% chosen were red. Or 80% picked, maybe, because it is a random picking without looking. Okay? That's what that's showing. So each of them, it's kind of showing how many. So there was one at 0.15 as well. There was one that had 15% red. So would it be surprising to get a sample proportion of 7 out of 20 or 0.35 like we found, or smaller, if we do this? Justify your answer. This is where we look at where 0.35 is. 0.35 is here. So everything at 0.35 and less is there. Okay? Now, I don't have the numbers here, but that's going to be definitely more than 5% of all the data. I don't have the y-axis to really tell. So, no, it's not surprising. Because more than 5% of simulations showed that. Okay? So based on your previous answers, is there convincing evidence that less than half of the chips in the bag are red? Do we actually think that she's lying? No. Because of the reasoning right there, boom, we're going to say this is likely just sampling variability, which is a natural thing. Ultimately, things regress to the mean, like we've talked about regression lines. The more you do, the closer and closer it's going to get to that 0.5, which is clearly the center of this distribution. Now, that was a whole bunch of different things related to what we've learned before and what we're going to be learning in this chapter, and that is an introduction to sampling distributions for today. See you next time.